Okay, guys, so just like I was saying, so I was working on the same problem to solve for the second solution, and generally in real life, you ignore the effect of the skin. So I started to solve this problem using the same file. So if you want to use it here, I'll show it to you. You see, this is the base, this is the thickness, this is the length. I guess this is one of the area for the Q sub naught. This is the position from the neutral axis to the points 1 to 6. I find what is the stress. No, after the stress, you find what are the P's, you find what are the Y with the taper ratios over here. We find what is the Vy of the wing. And when we have the Vy of the wings, we calculate the shear flows in the cells. Yeah, making the cut. Then we need to add the Q sub naught over here after making the cut. This is now same angle of twist because this one is statically determined. Correct? All right. So I substituted here with this equation here, the moment external, internal, and basically I got this equation over here. Okay. So basically I got now the values, which, oh, now it's giving an error. Okay. So, oops. So I guess. Is that one maybe? It's the same thing over here. Okay, so look like now is this one over here, we use case 1. All right. And then I did the same thing. So you see Q6197. And then I did this one so that with the second method, which is what I want to do today. So now this one is 55, like the other one with the other one. Okay, so let's see what's happening in this one now. Okay, so I'm not taking those. I was checking some stuff over here. Okay, so forget about this stuff. Yeah, I was trying to do in order not to have to redo it, to do the other one. Let's see. Hopefully that would work. That should not change. All right, here we go then. What is happening here? Oh, okay. So you see, that's the same thing that we got. So that's the 97. What did we get before? Do you remember? The 97.22, no? Okay, all right. So basically, let's do the second method, but let me just first summarize the results for the method 1 over here, okay? All right, so let's go over here. I don't have the notes, I'm gonna have to use this. And that's not gonna be pretty. All right. Okay, so example over here. If the previous example is solved ignoring the contribution of the panels of the skin, let's say, in resisting shear, which basically is case 1. The solution follows the same procedure, but IXX, instead of being equal to the 1080 we were dealing with, all right, so let's see what we have. Let's put on top. IXX would be 1, 2, 3, 4, 5, 6. So 540, 10 to the 6. Millimeters to the 4th. Okay. Okay, so let's do again. I'm going to be repetitive, but repetition, I think, is the way to learn. If you remember what is the procedure, we had our structure. So I don't have here the figure, guys. So I don't know. Maybe I have it. It was 13. Then I have some. So 11, 12. So if you remember, this is the problem we're solving, no? Yes? Okay. So we have here, you see, it's taper on the Y, it's taper on the width, and in the prime-wise direction. Okay. So we were asked, knowing this wind structure, wind box, having the shear force over here, find what will be the effect at one section that will be right in the middle at 2 meters. Okay. And that's what we solve. And when we solve, you see we have the load, the dy, and we consider here the IXX to be the eye of the screen plus the one of the panels. Okay, so this is the stuff that's actually wrong, so that's why I redid it. But you see the process is to find the IXX, then you find the moments that will be identical, so this would be different. Okay, we found the bending stresses. After the bending stresses, we find the PCs, the PX, the PYs. We find the taper ratios. Okay, and we calculate these values over here that everything was summarized on the table. All right, and then we finished that the other day, knowing the loads from the tables. Here we go. We find the value of the shear force on the panels. When we have found the value of the shear force on the panel, we're able to find the value of the shear using the normal approximation over here. Okay, so let me give a little bit here of the kind of the same information. Over here, so we had here this. That this will be equal to what? Where did we do the cut last time? Do you remember? On the left vertical. Here, no? Okay. All right, so we said that this will be equivalent to doing this. All right, plus this of the interhand. Okay, so basically, if you want, I'm just going to copy now from the MATLAB, but you have the expression. So here we go. So let's see, the IXX was 140. I might try to unselect some stuff. All right, so let's come over here. I'm going to unselect this one so you can copy. So basically, I'm going to select a bunch of this stuff here. Yeah, I'm going to select everything to tell the truth, so we can just copy. What can I? Somebody knows what is the shortcut to execute the file? F5. Okay. All right, so here we are. Okay. So from here, we're gonna have okay, so let's do a quick summary. So let's say mx, but vy equal to 10,000. Mx equal to 1, 2, so 1, 2, 3, 4, 5, 6, 7, 8. So 200, 10 to the 6, I guess is newtons, millimeters. The other one is going to be newtons. Okay, so we found, remember the equation is sigma equal m x over y divided by I xx for each one of the booms r. So over here we have that sigma 1, the bending stress, is equal to negative 111.11. So the top is in compression, negative 111.11. Sigma 3 will be the same thing. Okay, they should all be the same thing except for the sign. Up to 6, so negative 111.11 Newton millimeter square. Sigma 4 will be 111.11. Sigma 5 will be 111.11. Sigma 6 will be 111.11. And this again will be newtons per millimeter square. So these are, remember, to calculate the bending stresses. Bending stresses at L equals 2 meters. Okay, this is at L equals 2 meters. This is the value, and at L equal 2 meters, this is the bending moment. At L equal 2 meters. Sorry. Can I zoom out? This is way too big. Oh, good. Okay, so after this, I'm doing this so you can also copy the MATLAB code if you want, no? Okay, I'm showing on the screen for a reason, okay? So now you see what is the next step. We find here what is the taper ratio of dy over dz. So basically here what I'm doing is what we did in this lecture over here, or the previous one looks like, is what I did here on this lecture to find these values over here, no? Yeah, okay. So these are the dy over dz. You see one is 0.1, that will be the second one, and this will be 0.05, which is this one over here, no? Yeah, dy dz, dx dz is basically these calculations here. All right. So now that we know this, okay, but before that we did the pz. So then what did we use? We used the relation of pz sub r is equal to sigma sub r times b sub r. Okay. And what do we have? We have pz1, pz2, pz3. So it's just going to be a change in values. And pz4, pz5, PZ6 equal. All right, so let me go now to the execution file. So let's see what I have. I have minus 110 to the 3, so minus 110 to the 3 for PZ1. PZ2 I have minus 133.33 10 to the 3. Then minus 110 to the 3, so it will be newtons. PZ4, we could use the symmetry. Would be just the same thing, but with the reverse sign, so 110 to the 3. Newton PZ5, 133.33 10 to the 3, and PZ6, 110 to the 3. Okay, after finding the PZs, we're going to find the PYs that will be equals to the PZs times the dy dx, okay, the temperature. Okay, so this is like doing another example, guys. And I hope you're going to use this to do your own code, no? That's why I'm doing it, otherwise I will not be doing it. 2. Then we use the Py sub r's will be equal to the Pz sub r's times the delta y over delta z. And from this one, we're going to get Py1, Py2, Py3, Py4, Py5, Py6. Right. And this should be equal to, here we go, minus 5,000 minus 6. So I guess it's minus 6,366.7. 5,000. 5,600. Oh, 600, 6,000 should be 6. Yeah, I measured 160 over here. That's what I was paying attention. 6,666.7. And the last one will be again 5,004 PY6. So if you remember what we do all this stuff is that now we can find the shear force in the panel. Okay, we have the YW was equal to the Vy, which is the external, minus the summation of all our P sub Z, no, P sub Y, sorry. So it should be the 10,000 minus, you add all this stuff here, so it would be minus 5,000. Remember, just use the magnitudes. So what is that going to give us? 2.4 y. Okay, so it looks like I used the correct sign. So here. Okay, minus the summation of the these forces will be minus over here plus 5,000 plus 6666.7 plus 5,000. And this is going to give you that the force on the panel or the web is equal to 66,667. Yep, I guess if there's more values about them, okay, newtons. Okay, so next we find shear flows in cross section. So now, sorry for that. I know I should have done that maybe different, but basically now it's when we are here, all right, in this one here, all right. So we need to find here the Q's. What was the number in? I think 1, 2, 3. Okay, so we find the number in here. We know that Q61 equals 0. That's where the cut is. Then we use the relation, let's say Q12 is equal to Q61 minus Vy over Ixx B sub 1, Y sub 1. So we found that this one was equal to minus 33.33. Okay, similarly, I'm going to do Q3 will be equal to minus 77.77. Q34 will be equal to negative 111.11. Q45 minus 77.77. Q56 minus 33.33. Okay, and that's it. So basically here what we did, let me just redo a figure. I don't care about redoing figures, always good. This is our cut. 1, 2, 3, 4, 5, 6. Okay, we found the Q's over here. Okay, so let me do a figure again and then we'll move to the next page. So now, since we made the cut, what do we need to do? We need to find what is the internal shear Q sub naught, no? Yeah. In order to find the Q sub naught, what do we do? What do we do in the procedure? We equate the moments internal to external, no? Okay. So that's the procedure. So we know that. So let's see what did I do here on these notes. I took the moments. Okay, so I don't mention. So I guess Vy is over here. So it looks like I take the moment. Where did we take the moment last time? Did we take it about the middle? Yes.
So see, before we forget, let me put here instead of positive, let's put this one. Did we call that point here A or CG? CG, no? Okay. Let's see, remember, why it's important to take the moments about the CG? If you need to look at the notes from the other day, go ahead and look at the notes from the other day. So that we can cancel the effect due to all the PZs and PYs and PX, no? Yeah? Because otherwise we need to take them into consideration. So if we take the moments about the CG, now we only need to deal about whatever moment is created about the external force and whatever will be the Qs, no? Correct? All right. So remember the Vy was here. All right, so I'll show you the code. I think you should be able to figure it out. So you see the V external will be the Vy times S12. And then I do the Q12 times S12. That will be the value of the force times the arm, no? Yeah. Q23 times S23 times S3/4/2 will be the arm. I think that's exactly the same thing that we did on the previous note. So let's see, probably here. Taking moments about the centroid of the cross section so that these terms are zero. We take the moments here. This is exactly the same equation, but here we use the values, no? Okay, should be exactly the same equation. And so basically, if you want to summarize this, so let's take here. Let me make a note here. Taking moments about CG. Remember, it's important to take them about the CG. All right. So we do that. We found that the expression for the external moment is equal to, let's see. So maybe I should have the external as well. All right, so now we should have everything, I guess. Oops. Here we go. So for the external moment, we're gonna have, how many zeros do we have? 1, 2, 3, 4, 5, 6, 7. So let's say 60, 10 to the 6 newtons per millimeters. And for the internal, this is gonna give us a 140, I don't know how many zeros, 10 to the 1, 2, 3, 4, 5, 6, 7. So 140, 10 to the 6 minus 144, 10 to the 4 Q sub naught. All right. So next it says solving summation of external equal to summation of internal for Q sub naught. That gives that Q sub naught is equal to 97.22. Newtons per millimeter. Okay, so we can say at the end, the final distribution is, if you want to use the Q bar 12 equal to Q12 plus Q sub naught, you can, or you can use the figure Q bar 23 equal to Q23 plus Q sub naught. Q bar 3,4 equal to Q 3,4 plus Q sub naught. Q bar 4,5 equal Q 4,5 plus Q sub naught. Q bar 5,6 equal Q, Q 5,6 plus Q sub naught. And Q bar 6,1 equal Q 6,1 plus Q sub naught. And this one we know should be equal to 97.22. So let's see, Q12 is going to give us 63.88. Q23 19.44. Q34 minus 13.89. Q45 19.44. Q56 63.88 or 89, whatever you want. It doesn't matter. Okay, so again, let's do a figure because we always do figures. So one, two, three, 4, 5, 6. So let's see, Q12 is positive, so 63.88. Q23 19.44. Q34 goes in the opposite direction, 13.89. Q45 goes in the same direction, 19.44. Q56 63.88. And Q61 97.22. Okay. Any question? Basically, it's the same thing that we did the other day, okay? That's why I went so fast. So if you want me now, what I'm going to do is, let me open this big and large file, open method 1. I'm going to scroll through it very slowly if you want, so you can copy it if you want. Obviously, there's some comments over here that I'm going to delete. If you want, you can. I mean, let's keep it this way because if you need to modify it, maybe you can modify it. So, for example, let's say now that you have the same problem, but instead of being statically determinated, it's statically indeterminated. What do you need to add to the present code? The angle of twist equation, no? This section here, and then you need to solve not only for Q sub naught, but for Q1 and Q2, no? Yeah, but everything else should be the same. So you see here, it looks like I took one of all codes and I kind of deleted it, but you might have to update this stuff. Okay, now this one is gone. Let's go for the second one. For the second one, let's go through the figure again a little bit. So if you remember the procedure, here we go. All right, so you put over here, wait. Continuous. Next page. All right. So here we go. So method 2. If you remember, we discussed on Thursday, so probably some of you have forgotten a little bit about it, that another way to solve the problem will be to do what? Okay? I cannot derive something that probably you derive this in solid mechanics, that if you have any type of beam structure subjected to a loading, and if you take one element, what do you make cuts so that the internal actions become external, no? When the stuff become external, then you can use summation of force equal to 0, summation of moments. But if you look at this one, this will have a shear force here, and then it will have a different shear force on the other side that are referred as V plus dV. And the same thing will happen for the moments. Okay? So we say that in structure, the equations of equilibrium, summation of forces to summation of force equals to 0 and summation of moments equal to 0, still need to be valid. All right? So in order to be valid, there is something that you need to add to the structure, which are the shear stress, that then will make these two equations satisfied. Okay, so the approach now is to do what? So we have here a beam. Imagine about our structure. We can calculate the moments, let's say at this cut, and we can calculate the moments at this cut, correct? Okay, and then we can calculate the shear stresses at each part of the cuts, no? That's what we're seeing over here. All right, and then you will find out that the shear flow basically will depend on the value of the force. So the force is equal to the same as we did. The sigma times the area of the stringer. Okay, I use B's, but here I put A. And then the shear flow will just be the difference between those two forces divided by the length over here, dz. Okay, so this is a very simplified way how to explain it. Do you have any question about the concept? Because now what we're going to be doing, we have this over here. We need to calculate here at 4 meters, no? At 2 meters, correct? What we're going to do is, instead of calculating everything at 2 meters, let's say we're going to calculate everything we're going to calculate the moments and the cross-sectional area at 1.9. I'm going to calculate the cross-sectional area and the moments at 2.1. Okay? And then we're going to calculate the sigma 1 at sigma 1, sigma 2, sigma 3, sigma 4, sigma 5, sigma 6 at those two locations. Is that okay? Yeah, okay. So let's do that. So that's basically what I did on the code. So let me go here to method 2. All right, so method 2, we have like let's say here side view. Might be easier to sketch. So side view, let's say we have 4 over here, and okay, let's do 4 and 2 over here. It could be side view or top view, I'm not that sure. All right, so we know that what we try to find here is at L equals 2 meters. So what we're going to do is we're going to make a cut here at, so let's say it will be 1 at 1.9 meters, and 2 will be 2.1 meters. Okay. Okay, so I think, again, like I told you, I did this the other day before leaving home. So I did everything straight into the MATLAB. I did not take any notes. So let's see. I think I did all the notes over here. Yeah, so you see here. Okay, so let me understand what I've done over here. Okay, so let's see here at cut 1, which basically means that L equals 1.9 meters. Okay, I'm gonna leave some of the calculations for you. So at that cut, what's gonna happen to the cross section? We're still gonna have the cross section 1, 2, 3, 4, 5, and 6. But because this is taper, at the one point that you have the width here, this width over here is 1.18 meters, and the height is 0.59 meters. Okay. If you remember, what were those measurements at? We go back to this problem. If we did the cut at 2, you see this was 2. What did we have at 2? We had 1.2 and 0.6, no? Yeah, now we have what? 1.18 and 0.59, no? Okay. All right, so if you do this, so now for this cross section, what are you gonna have? So for this cross section, what do you have? I x1 will be equal to the summation of the b sub r's y sub r squares, where the y sub r's will be what? Wait, 0.59 divided by 2, no? If you don't understand something, please stop me, okay? But we need to do the same thing distance from the neutral axis. Yeah? Okay, so top and bottom will be half of it, no? So if you do this, probably you see here what I did. I just kept changing here the values for ix1, x2 with these values here. You will find that ixx1 will be equal to 5.2215, so 522.15, 522.15, 10 to the 6 millimeter to the 4. Do you understand? If not, stop me, okay? This is the time to stop me as many times as you want. Okay? And so maybe do I put other values for the first one and then we move to the other one? Okay. Yeah, let's do maybe that. I'm going to change a bit of the order that I have. And now, what would be the moment created at this point? If you remember before, we found the moment to be equal to what? Oops, no. What was the value of the moment? We did 100 times 2, no? Now we need to do 100 times 2.1, no? Okay, so I will give us x. Or did I reverse this one? Okay, so I think I reversed this one, no? Good, I'll check this with you then. So x1 is 1.9. So let's see what one should be higher. So 210. And 190. Hopefully that number will change. At 5. That change everything, no? Yeah, that sounds familiar. Okay, so let's see what I've done here. Let me undo this one. Control Z. What did I do now? Okay. Okay, so let's see. Maybe did I change this one? Maybe I choose the other here. So is this from the wall? So 1.22.
Okay, so let's wait for the moments. We'll figure that later in a minute. All right, so let's start this one. Now we go to our cut. To this was the 1.9. So it depends on what we do. Okay, so at L equals 2.1 meters. Yeah, so I know what happened here. Is that I made the cut from the tip instead of the wall, the distance. But it's fine. And we figure that out now. So we got this. Yes, yes, but I think here I did the reverse. One, two, three. Okay, so for this one, what did I say? I have 1 point. So you see, I did the, well, this is from the wall. Okay. 2.1, 1.22. And the height over here will be 0.61 meters. And this will give us an IXX2 summation of B sub R Y sub R square equal to, you see I said it here, 558.15 10 to the 6 millimeters to the 4. Yeah, so I know what's happening. So sorry for the confusion here. So now, if we look at the figure here, we see we did here the moment. So we're gonna have the moments over here, no? So the closer to the wall, you see it goes here on the linear, no? Yeah, so we can get from this figure. So you see then, if we look at this one, then we can get these two values over here, no? Yeah, just from the figure. I mean, you can do the values if you want. So we get that. So from here, we're gonna have X1. What do we have here is 190. 10 to the 6 newtons per millimeter. So MX1. MX2 equal to 210. 10 to the 6.
On the paper, we're doing measurements from the wall.
What happens here is that I do two different ones. So you need to look from here. You need to look at these figures here on the variation.
Right.
Okay.
So cut one is at 1.9 meters. So going to be 210.
Yeah, but the force is applied here at the tip. So that's what I'm saying is reverse. So the measurements here are from the wall, but here when we calculate the moments, they're really from the tip. Because the force is being applied here.
Right.
You understand what I'm saying? I thought it was clear, but did you understand what the confusion here or not? The force is being applied here, no? So the moment will be this force times this one, no? So really 1 is 2.1 and really 2 is 1.9.
Right.
Okay. Yeah, okay. I think, okay. So the problem is when I say 1 and 2, I was considering the origin from the wall. Correct? Now that I'm doing the moment is what? Force times distance. I'm doing it from the tip. So the 1.9 is really what? 2.1, so that would be the 210.
Right.
And that's what we have here, the. Oh, hold on, what I'm saying. So MX1, but this one was here, you see it's before, so now this one is the 210.
Right.
Oh, okay, so what happened here then?
So the MX1 should be 210 because it's 2.1 from the wing to everyone.
Yeah, but then yeah, correct, but then I was here, the distance from here. Except these measurements, so now let's look at the measurements, so one should be, oh. Okay. Figures, okay, so which one should be wider, 1 or 2?
One.
One, on this figure, which one is wider here on the figures I've done? 2, so I switch this order. So good question, so how do you want me to change this stuff? You want me to put here 2 and 1 or change the numbering on top?
That's the quickest way.
Yeah. That's the quickest way, but I'm asking you, so I've got 2. I've got 1. But then the notation becomes so. I mean, we have to leave it that way, okay? Otherwise, it's gonna have to change everything. Sorry for that. It's just my confusion from doing the notation. Okay, do you understand what's happening? If not, don't feel bad, okay? I'm sure you're not the only one. All right, do you see what's happening here? Okay, good. Okay, so now that we have this, we can calculate what will be the stresses. So I'm gonna do again the bending. So let's do first bending at cut 1. Funny, so it will be all these values here. So we have to change all this stuff by 2 by 1. Okay, let me change the code. It's going to be a lot easier. Because the only thing I need to do here is, no, so this is correct at 1.9 meter, and this is correctly on the code. Yeah, so everything will be correctly on the code. All right. So let's just follow the code over here. Now I'm just going to give you these values over here. Okay, and these values over here. All right, so I want to say over here. The bending stresses. That's 1 and 2 are. So I could use more complicated than the other method, but I think after that it's a lot easier. So basically what I have here, let's say cut 1, just change a bit the notation, sigma 1, sigma 2, sigma 3, sigma 4, sigma 5, sigma 6, cut 2, sigma 1, sigma 2, sigma 3, sigma 4, sigma 5, sigma 6. So it's going to be very repetitive. All right, so that will be 17.34. One of 7.34. One of 7.34 minus 107.34 minus 107.34 minus 107.34.
Okay. Oops. Yeah, that's correct. $114.75, there's gonna be $114.75, $114.75, $114.75, negative $114.75, negative $114.75, negative $114.75. Now what do we do with this? What are we gonna do with this with the stresses? We're gonna find which piece. What are the same procedure as before? Which piece do we find next? We should find the PCs, no? What should be the PCs should just be that times the area. So you see, this should be just times the area. So the PCs of R will be equal to the sigma sub R times B sub R. All right, so we do the same thing again for cut 1. We do the same thing for cut 2. We're gonna have PZ1, PZ2, PZ3, PZ4, PZ5, PZ6, PZ1, PZ2, PZ3, PZ4, PZ5, PZ6. Okay, so this is going to give us PZ1 is, I'm going to put the notation as it is, so then 9.6610 10 to the 4. So 96,610. The one will be 128,000, so 1.2881 10 to the 5th. PZ3 will be same thing as that one, 9.6610 10 to the 4th. PZ4 will be minus 9.6610 10 to the 4th. Then PZ5 will be the 1 to 8, no? By symmetry. The negative minus 1.2881 10 to the 5th. And negative 9.6610 10 to the 4th. Okay, and I've got 2. We're gonna have 1.0328 10 to the 5th. No, yes. Yeah, 1.3770 10 to the 5th. 103, 1.0328 10 to the 5th, and then it's just going to be symmetric but negative, minus 1.0328 10 to the 5th, minus 1.377, ten to the 5th, and 1.0328 10 to the 5th. Newton energy. Okay, so let's go a little bit back here to read what we are doing, okay? All right, so let's say here you have a string at the top and a string at the bottom between 1 and 2, no? Yes? So we found what is the
stress at this location and what is the stress at this location. Okay, what are the units of stress? Force divided by area, correct? So in order to find the force in that direction, over here you need to multiply the stress by this, by the area of the stringer. Yeah, here you need to do the same thing. You need to multiply then the stress by the area of the stringer. So it will give you the value at this point and the value at this point, no? Correct? Okay. So next, the change in force over here will be whatever, P1 minus P2 or P2 over P1. So that is what we're doing next. You see over here the DPs. So let's see. Difference of PZ along the distance 0.2 meters. Okay, so it will be 200 millimeters. So I do the DP. I define here the DP as being PZ, so force per unit length. So I do DP. I don't have the value for DP, so I'm going to do DP divided by DZ, okay, for each one of them. All right, so if you want, here let's start. Difference in PZ along the 0.2 meters, which is the 200 millimeters. So the difference of the first stringer will be, let me call it here delta P1 instead of DP1 will be equal to PZ1 cut 1 cut 2, so minus, let's say, PZ2. It will be cut 2 cut 1 over here, okay, for these values, divided by DZ. And we do the same thing for every single one. So delta P2 will be equal to PZ2. Oh, what did I do here? Both of them are PZ1, sorry. So PZ1, this will be PZ2 minus PZ2 divided by DZ. Delta P sub 3 will be PZ3 cut 2 minus PZ3 cut 1 divided by the length of the cut. Delta P4 will be PZ4 minus PZ4 divided by DZ. Delta P5 would be PZ5 minus PZ5 divided by DZ. Delta P6 would be PZ6 minus PZ6 divided by DZ. Okay, and that's given here. Let's see, 33.343. For the first one, 44.457. $33.343, so the same thing as before. So the one should be the same, but with the opposite signs, no? Will be minus 33.343 minus 44.457 minus 33.343. Okay, I'm going to do a figure because otherwise I'll get crazy. I mean, the reason I'm doing this is because I taught method 2 on the assignment, no? So that's the only reason I'm doing all this stuff, so you can copy. So if I do a figure of this, let's see if I can make this having some sense over here.
You do a figure here. So can do two. All right. What did I do here? Oh, I did it wrong. No, it doesn't matter. Yes. I didn't do a good figure. So maybe, I mean, it doesn't matter. I think we're going to recognize what I'm trying to say. The figure is not good at all. So I hope you do it good. You should have two at the back if you want, not three at the back. Okay. Maybe I can do this now, something like that. Okay. The only thing I was trying to say over here is that if we look at this, if this is 1, 2, 3. Yes, sorry. 1, 2, 3, 4, 5, 6. Okay. I don't want to talk too much on this figure here. Right. The other thing I'm trying to say is that what is really happening? What is this 33.3? This 33.3 here indicates what? That this will be here. So let's say this will be already see P and 1. So let's say will be 33.343 pushing over here, and this will be 33.343 on the opposite direction, no? Okay, we could do the same thing over here. This should be what? 44.457, and this would be 44.457. Okay, and this one will be the last one, will be 33.343. Okay, do better figure than me. Okay, and this one could be here 33.343. Okay, so let me ask you one question because then I will be very easy. Because I think that's your assignment, no? On the assignment you only have 2 cells or you have 1 cell? I remember.
1 cell on the left.
But you don't have an extra stiffener here, no?
Yeah.
Okay, so now if you don't have an extra stiffener, then what should be the Q over here? If you didn't have this one, what would it be? It would be the 33.343. Yeah, that would be basically your Q, no? You are about resistance, okay? But because you have this one, you're gonna have an interference. So this one is a lot more complicated. So, all right, let me do a figure, another figure. The one on the assignment is a lot easier. So the reason I'm trying to say is this: don't take the assignments and overcomplicate it. All right, that's the only thing I'm trying to say here. Yes.
You might run out that.
Yeah. Yeah. So now, what I'm going to do is again a figure here. All right, so let's say here this is. So in here, we're going to look at this one over here. All right, so we're going to look at $44.457. Okay. Now, so we're looking at this one here, no? Okay, I'm just doing the top one. Here, okay? Yes. those two panels over here are these two panels over here, no? Yes, I'm doing this. Looking at this one, I have this one, okay? So what does that mean over here? If I do the figure, I'm gonna have here A. We do it this way, this would be the Q12 will be this way, this way, this way, this way, this should be Q12, and that's up. Then on the other side, we're gonna have what? This way, this way, this way, and this way, and this will be Q23. Okay, so let's say we look here at this point over here. There's different ways to do it this one, but let's say here at this point over here, okay? Point, or if you want to think about, I like to think about this, about like electrical engineering. Okay, so at the node, what is coming in? What are you gonna have? You're gonna have 44.457 plus Q23 minus Q12. Yeah. Okay. Equal to 0. So basically you do summation of forces at the node. So now you can rewrite this. You can write Q23 as being equal to Q12 minus 44.457. Okay, now I'm going to do something similar with the 3. So this is 3. I'm going to have here the side panel. And this will be this panel over here, okay? So now, what is the force on this one? How much do we have on that one? 33.343. Maybe let me close up this stuff here. Sorry for that, guys. All right, I'm here over here. Now we have 33.343. And again, everything else is identical. So we have here. So now this will be Q23. Okay, if I simplify. And this will be what? What should be that one? If you look at the figure, that should be Q34, no? Or 43, no? Yeah? Doing this panel and this panel. So Q34 or 43, whatever you want to call it. And the same thing, we say at the node or point, okay? We have what? 33.343 plus Q34 minus Q23 equal to 0. So here I'm going to have to go to the code. But basically what we're going to have here is Q34 is equal to what? will be equal to Q23 minus 33.457. What did I do here? 33. Oh, 343. Yeah. I was looking at the top one. 343. Thank you for being good attention. Now, basically, what I'm doing is what? What is the Q? The Q1, the Q23 is equal to what? Q12 minus 44.457 minus 33.343. So this is going to give you that Q34 is equal to Q12 minus, no idea. Whatever, I mean, we can almost do it. Let's see if the code is doing it. So that's basically what I'm doing next. I'm guessing. Yeah, that's what I did over here. How much is it?
77.8.
77.8. Okay. But do I have that on the code? That's what I want to look at. Is this 77.8? Yeah, 77.799. Okay. So basically, I mean, if we do the same thing, let's do one more. Can we just do one more together? Because we finish at 1, no? All right, so let's do one more. Or if you want, I mean, I'll give you the choice at the end. So we can continue tomorrow. So let's do one more panel. So let's go now. To which panel do we go next? We did this one, this one. Now we can go to this one, and this one, no? Yeah. So let's go to that panel. So let's see. So let's do this panel here. I mean, I'm going to do the same size, otherwise too complicated for me. Okay. We do that panel and we do this panel here. Maybe get a bit bigger here and here. And here, and this time we'll be looking at this one over here. I mean, this one is the same as the other one, so 4. Yeah, so we're gonna have to look at the top here. We're gonna have the Q. For 5. The Q34. But now what are we gonna have? What should be the force? Now the force should be going out. No, here should be the 33.343. So again, at the node, what are we gonna have? Oh, wait, this one. Do we need this one here? Yeah, we need this one. So what are you gonna have over here? Okay, so this one is leaving, no? 343. So the only thing I'm not sure is about these ones here. So it would be that one. All right, let's see here what's happening. So Q45. Okay, we'll see what happened here. Minus Q34 equal to 0. So we're gonna get basically here we're gonna get that Q45 is equal to what? Negative 33.343. Minus Q34, which is minus 33.343. What is Q34 minus Q12? Plus 77.8, no? Because it's minus, no? Q34 was this. So we're gonna get that Q45 will be equal to much. So what is the difference on the sign? I think it should be the 44.457, no? It is 44.457 more or less. Because that's what we did over here, no? Now we are subtracting the other one, no? Okay, so it should be minus Q12 plus 44.457. One thing is bothering me here. Okay, there's one thing here bothering me. What do you think is bothering me here? By symmetry, what should happen with these two? They should be equal, no? So obviously, we have a problem here with just with the sign, no? Yeah. Okay. So let me look at this and we continue tomorrow. Anytime is the time. I will finish tomorrow. So I think the assignment is due on Thursday. Is that correct? So guys, what about for tomorrow? Try to do part 1. Is that okay? And then we can finish this one. And if you want, we can start the part 2 of one of the assignments. Is that okay?
Yes.
All right. Because you see, it's a lot of work, no? And it's easy to do mistakes on the sign. What did I do wrong on this one? Anyway, I need to get going.
They are saying that better than possible.
I think after Tuesday, I want to like as soon as because